Welcome to Build with Nas. My name is Nas. I'm the founder of Rebel and maintainer of the Rebel Open Core repo and also a bunch of text user interface crates which are published from that repo, including a terminal async crate which allows you to create any kind of REPL or shell that's fully async in Rust. This week actually I got an issue about a deprecated crate which I had to remove, and that kind of prompted this video because while I was going through that I was like, I thought it would be a good idea to kind of talk about Rust memory addresses and sizes, and just a collection of ways in which those can be easily used. So this is actually the issue that prompted the this video. So there's one of the companies that uses the Rebel Open Core repo. Actually, in their build system, they got a deprecation warning or Rust security warning for an unmaintained dependency, and turns out the dependency was get size. So this get size, the get size crate that was used by proc macro error had gone out of date, and this was, I think, sin version 1, and there was some crates in the Rebel Open Core that were actually pinned to this particular version. So one thing I did was I ended up removing the dependency on get size and replaced it with a different crate. I think it's this one, size off, which is actually a similar kind of thing. And this one is no deprecation warnings or anything. So I end up running, I think it's cargo deny and cargo unmaintained to keep track of what's going on with these dependencies. So there's cargo deny. This is all set up in the Rebel Open Core repo and the build scripts. So this also happens in CI/CD, and you can run it manually if you clone the repo to your system. And the instructions are all actually in the readmes for each one of these crates, each one of these folders, which maps to a separate crate. So yeah, there's cargo deny, which was I think flagging that this error warning, and then there's also cargo unmaintained, which is another one. There's another one that kind of uses heuristics to determine which one is maintained or which one has gone out of date. So I think this one was, this is maybe this is some cargo unmaintained. Who knows? But yeah, one of those two triggered this. So anyway, so that's kind of like the inception of how this came about. But so I ended up switching out of what was it? I got rid of the get size crate dependency in the whole repo and switched to size off. And then I was like, well, might as well do a video on memory address and sizing for so that the reason size off was even used in the repo is that when I'm actually let's see if I can demonstrate this. So when I'm actually running, for example, the TUI, let's see this. Okay, so here I say new run log, that starts the logging system, and I say new run example. So when I'm running the examples in the TUI crate, I can actually, the log output has the size of all the data structures that are used in the system. And so the TUI engine, so this is a great example. So here we have the TUI engine where this is essentially there's a bunch of analytics that are reported in the logging system, like the frames per second, the size of something called the off-screen buffer. That's the size right there. Then there's the size of the contents of the editor in memory and the size of the editor buffer history, which is like an undo redo buffer. So essentially you can see, like, if you add like a character here, like that changes the size. So X, Y, Z, something like that. So essentially, as we modify the mutate this editor content, the logging engine reports the size. So a lot of the stuff actually comes from there's a bunch of structs that are used by Rebel Open Core, each of which has to implement a particular trait. And I will go into all of that in this live coding video. So it's actually not going to be a very big video. A lot of it was just background information that has taken a bunch of time, but the actual video should be pretty small. So let's start a new project. So I just created a new crate, and this one is, we're going to add some dependencies here. So let's see, I think I'm going to do, so cross term is just so that we can pretty print stuff, and size off is this this crate that I was mentioning. So let's make oops, let's do this. Let's see, let's do, oh, actually it should have been I meant to do this as a, not a binary crate, but that's okay. So here we can actually stub out a couple things. We're going to have some test utils module where I'm going to put some functions to format output, so it's not so verbose. And then we're going to do some stuff with memory address. So this is going to be like, how do you get the address of like a variable in the stack? What if it's a vec? What if it's a boxed? What if it's a box? You know, how do you get the address of not just the reference or the variable in the stack, but also what it's pointing to in the stack? What's the memory address of that? And then finally, we're going to do some examples showing how do you size things using the standard library, and what are the limitations of that standard library sizing, and then when is something like size off useful. So with that, let us do this. I'm just going to bring in this test utils because there's really nothing that interesting here. This is just I had a different video earlier on. Where is it? I think it's this one. Oops, this one. Just close these. I think there's like box. Yeah, there's like box and pin. There's a bunch of videos on box and pin, and there's also articles on Developer Life for box and pin. So those are kind of like also related to memory address and things, but this one is a little bit more concise and scoped to just address and size. So let's see. So there's our. So essentially, we make two functions, and all these functions do is quite simply they use cross term to format. Just basically take a given, in this case, the memory address, and then it just calls the format macro and formats it with bold and white. And there's another one that does it with green, and then just puts the word bytes. So nothing that interesting here. So let's go to memory address. This is the first one we're going to do. So let's do this. So to get started, there's actually a couple of different ways in which we can get the memory. So I'm sorry, we can get the address of a variable, and I'll just walk through each one as an example. And then let's see. So let's start with this. We say in our test, we're going to say get address of variable on stack. So that's going to be one thing we're going to do, and then we're also going to have get address of box on heap, and there's one more, which is going to be, I think we're going to do get address of vec on heap. Yeah, that's right. So Excellent. So let's start with get address of a variable in the stack. So let's make a variable. And actually one thing I want to do is also grab these here. This is just stuffing out a bunch of stuff. Okay. This is the test fixtures that we had added here. It's just a bunch of functions to format things. So that makes it a little bit less noisy. So let's make a value and let's assign it 42. So how do we get this is actually fixed size. This is a scalar type, and the size is known. In this case, it's usize, which is 8 bytes or 64 bits, because I have a 64-bit CPU. And so here, if I wanted to, let's see, let me do this. If I wanted to do this, we can. One way to get the memory address is this thing called the as const t syntax. So here we can do something like we can get a reference to the value, and actually it skipped a couple of steps, and then we can say the pointer that we can actually cast this reference as a pointer. And this pointer, what the syntax means is that let me write down what the syntax is. So it's a we're converting the reference to a raw pointer. Let me put this here. So this one is, oops, yeah. So what we're doing is that we have let's see this thing here, just to clarify a little. So we have const t, which is the immutable raw pointer, and what we're doing is that this syntax as const, in this case usize, what it does is that it oops, this is usize, and what it does is that it converts the reference, which is this ampersand val, to a raw pointer, and the type of that pointer is const star const usize. And the star const usize in this case, or any star const t, is a raw pointer to an immutable value of type t. So that means that we cannot modify the value that this pointer points to. So it's similar to a reference, which also gives a read-only access. So, but that's just gonna break down like what this thing actually means. So once we've gotten this raw pointer, which is immutable, then we can actually just dump it. So basically, there's our pointer, and if we wanted to display it, we would say the address of value is this thing. And if we run it, we're going to see that it says the address of the value is this hex number. So this is where on the stack this particular variable lives, and the size of that variable is 8 bytes. So we're going to get in the sizing in the sizing section. We're going to get into like how do we get the size of this variable. There's actually a standard. There's in the standard library. There's a size of and size of value macros which we can use. But for now, we're just going to stick to the address. So that's one approach. The as star const t. So another approach is we can use a. This is also in the standard library. We can use a this one, address of macro, and this one, it's kind of cleaner to me. Like I kind of prefer this syntax. If you notice, the size is the same. It just gives you the same star const t type when you call the address of macro. So it's just nice to do it this way. And then we can just print line the thing, and it should be the same. And so we can make our assertions, and then we can say assertions. We can say assert that whatever we get from this and whatever we get from that should be the same. And as you can see, it works, the address of the value, whether we used star const t, which is an immutable raw pointer to our reference in this the stack, or whether we use standard colon pointer address off, the results are the same. So here we can see standard pointer address off macro, and yeah, you can look at the source, and but yeah, it's pretty straightforward. And there's also address of mute, which is we're going to go through that again. There's another approach. So this is the immutable variance of our approach to get the address of this variable. So the variable is again 64 bits or 8 bytes. It's on the stack, and we are getting the address of where that variable lives on the stack. That's what this is. And then what we can do, another approach to doing this is we can say we can use so this is going to be a little bit different. This is instead of the const pointer, the raw pointer coercion, we can do mutable pointer. So that's what this is. So basically we're saying, oh, and this is red because it's saying, okay, you can't do that because oops, that's wrong. That's not right. So what we want to do here is we want to make a mutable reference and just cast that, just like we did. So let me just make this a single line so that it's, there we go. So here we have like a reference that we're getting to val, and we're casting it to a const t, and here, or star const t, and here we're casting a mutable reference to val as star mute t, and so it's complaining that this is not mutable, so we could just make that mutable. There you go. So this is very similar to as star const t, but this is as mute t. So this means that whatever we get from here is going to be mutable, but at the end of the day, when we print it and we make an assertion, it's going to be the same. So as you can see, the hex addresses are the same no matter which approach I take. Even though, you know, this is immutable and that's mutable, it doesn't matter because a lot of that information is static typing. That's for the compiler while it's doing its checks, and then once the actual binaries get generated, none of this actually exists in the assembly that comes out. So approach, let's do another one. This is kind of similar to this. We're just going to use the standard libraries macro just to make it a little bit readable, more readable. And then if we run this, so basically we just said address of mute, same kind of thing, address of mute, and then as you can see we get a star mute t, and here we also get a star mute t. So these are the same. These two types are the same. These two types are the same. So these approaches are equivalent. We can even say 1.1, and we can say approach 1.2, and here we can say 2.1. We can say 2.2. There we go. That's, I think, a little bit more accurate. So now if we run it, we should see the same exact address, and lo and behold, no surprise there. One last thing I want to show, because I'm running out of ways to do this. Finally, we can use this, the print line macro. It actually has a facility to print the pointer actually. So what we can do is, here we can say pointer 5, and we can get the, we can do format, and we're going to say to format. So what we're telling the format macro is that use this format, I forget what the name of these things are. It's not even, oops. Let's see. I think it's like a format specifier or a format syntax documentation. Those things in the curly braces. I think they're called these things. Positional parameters. Let's see, parameters, formatting parameters, formats spec. Okay, I think that's what it is. So formatting parameters that are the format spec. Okay, cool. So yeah, so we can use the :p formatting parameter to essentially tell the format macro to transform this into a memory address. So here, because all the other ones have been, what we can do here is then we can say print line, and when we make the assertion, we have to say actually it's not going to work because oh no, it's actually will work. So we can say assert. So unfortunately this is a string and that's a star const usize. So what we have to do is that we have to apply the same format specifier here. So we can just say to pointer, and that should work. So if we run this, as you can see, oh, the bolding went away. So that's okay. We can do bold and white. It should work. Oh, and this, it moves it, so we have to say con. I think that should work. Yeah, there we go. Perfect. So there you have it. This is the 5 different approaches to getting this. And let me put the docs up here. So this is like essentially a bunch of information about what we just did. There's like the star const t, the immutable raw pointer, star mut t, the mutable raw pointer, and there's essentially 2 ways of getting it. We can either cast it directly to this and that, or we can go through the macro. That's what this is. And finally, we can use the format specifier of the :p to the format macro, and we can get the address from it. And then this is jumping a little bit. So there you go. That's the all the stuff related to variables on the stack. So now let's move into the heap and then see what that looks like. So for heap stuff, let's put that here. Actually, I'm just going to merge the documentation. So that's so far what we've done is the heap stuff, and this is so this much is the stuff for the stack, and this is the stuff that we're going to do for the heap, but we'll come back to that in a moment. So let me just copy this for the repo, because I publish all of these to the Rust Scratch repo, so it's easy to get to this one. So here, if you go to the Rust Scratch repo, you'll find, and links to all of this I'll put in the description of the video. So it's in here somewhere. I forget the name of it. This one. That's the one. Okay. So now that we're done with this stack thing, let's do something a little bit more complicated, which is how do we get the address of a boxed value? So the fundamental difference here is that the box is gonna, it's the box, it's a smart pointer. So there's a piece of it on the stack, and what it's pointing to is on the heap. So even if I have a box of usize, I'm not actually allocating the usize on the stack. The usize is allocated on the heap, and I grab its address and I stuff it in a stack with some extra information, and that's what a box is. So we can say my box of usize, and that's what some value in it, 10. And then if we want, how do we get the address of the box? So so we can do this. We can say, so the address of the box is, we can get a reference to the box. So that's my box. And then we can get the address of it. So we can say box address, and remember that format address thing. So what this does is just takes the reference, and it just calls the format macro on it, and that's pretty much it. So essentially, this is one way in which we can just print the address of the box. So we could say, and let's see, this one's, oh, there we go. So 0x something. So that's the box, but that's not where the value of 10 lives. The value of 10 lives on the heap. So let's refine our message a little bit. So here, let's say now we want to get the address of the item that's the thing that this box is pointing to, that 10, the U size. So what we can do is we can say, in order to get the reference to the value, which is on the heap, we can say my box as ref. It's a big difference between, like, if you look at this, the type of this is ampersand box U size, and if you look at the type of this, it's ampersand U size. So you can see how they're different. So this is actually giving me an immutable reference, shared reference to the value. So then what I can do is I can then get the address of it, just like that, just like, you know, we did here, because nothing different here. And then I can print that to here. So this is the address of the value inside the box. In other words, this is on the stack, and this is on the heap. And then let's print this out and see what we get. So, so you can see, so it's address of value. I'm gonna make this line up so it's a little bit easier to read. So we have address of box is this, and address of value is some other thing, because this is on the heap and that's on the stack. So there, that's kind of like what I wanted to show. And then we can do this assertion. We can say that they're not equal, because they shouldn't be. If they're equal, we have a problem. So this is an example of using this is box as ref, and yeah, we're going to see how to do this with Beck in a minute. So so let's see. So we got, yeah, box reference, box address, var reference, var address, and then so if we wanted to annotate a little bit more with some comments, we can say like this. So the box ref is the address of the box itself. So the type is a reference of box, which is generic over type T. That's what this is. And then if we look at the type for the other one, it's quite simply, it's a reference to T, so ampersand T. So yeah, the type system actually pretty accurately depicts like what you would expect. So it's pretty amazing to see Rust type system, even though it's I don't know, for me it took a little bit of time to get used to, but I'm appreciating it more now that it just like shows everything just like it is. It's pretty cool. Okay, so we got the heap in the stack. That's sorted. Now let's do one last example for the address, which is what if we have a vec? How do we get the address of that? So same kind of thing, like what's the address of the vec, the struct that's on the stack, and what's its backing store, which is heap allocated, which is on the heap. Heap allocated heap. So let's do this. So we say, let's make a vec, and then we're gonna say, so the reference, this is just like before, just like a box. So we say, okay, so how do we get the pointer to this thing? Well, one way is we can say, we can do it like that, just like we did earlier. We can say val ref as, we can say const vec usize, because actually it's explicit our type. So we can say vec usize here. Actually, whatever, vec 32. Whatever it is, these two have to be the same. So basically, whatever this type is that type. So we're just saying, okay, cast this to a raw pointer that's immutable of this type. And then, so as you can see, we see start const vec of t. And unsurprisingly, we can just print this just like we have been. So we say address of value, and then this is on the stack. And val is really the vec. So let's see what we get. Some address. So okay, that's great. And then what if we wanted to a different what if we want to use a different way to get this address? Because we know that we can. Because there's more than one way to do, instead of the casting of this pointer, if you think that's not the greatest thing to read, here's an easier way to do it. This is the same thing. You'll see from the types. As you can see, the type's the same. It's oops. Oh, that is not the same. Oh, let's see what we get here. So value as pointer. So it returns a raw pointer to the vector's buffer. So this is the thing that it's pointing to. Yeah, that works. Oh, interesting. So this one, let's see what the value of this is. So we say address of heap pointer 2. They are actually different, which is right, because this is this is pointing to the start of the backing store. This is pointing to, so this is, let's see, get the address of the heap allocated backing store, and this is where the first item in this vec is here. So if you think about the vec, it has a bunch of information in, like the capacity and the length, which is capacity is like how many it can hold, and length is like how many it's holding right now, and the start address. So this is the start address of the backing store of the vec, and the variable that we use to access that vec is actually this thing. And the address of that variable on the stack is this thing. The address of what that thing points to, which is the start of the backing store, the for the vec, is actually this thing. So let's see. So there's another way, instead of just doing this, to get the backing store, so that we can say like this is approach 1.1. And we can do, so this is basically what we're doing is we are getting the raw pointer to the heap allocated memory. So what we can also do is we can, because we know we can do that with similar kinds of things with boxes, we can do this. We can say, we can take the value and we can basically turn it into a box slice. So it's going to be, the types will make sense when we look at them. So it's actually a box which contains a slice of I32s. So the type is this thing. So we're basically doing a type conversion. We're saying convert vec of t to box of slice of t. And in order to get the raw pointer, this is the first thing we've done, and the second thing we're going to do is get the raw pointer. So to do that, we can say same thing, this as ptr. We can say let ptr3 equals boxed as pointer. And note these types are the same. Pointer 2 and pointer 3 are the same. Star const I32, which is the first item of the backing store, because where it starts. So it's pretty cool. And we print line it, and let's see what we get. So now if we print it, we should see, look at that, they're the same. This one and this one are identical. So if we make assertions to confirm that, we can say that, yeah, actually pointer 3 and pointer 2 should be the same. That's right, because this is the heap. This is the address, heap address, backing store. And we should also say that the let's see, pointer. Oh, we gotta do that format thing. Let's see, how did I do this earlier? Oh, okay. So actually, you know what? Let's just do this. We can do. I'm gonna cheat. I'm gonna say format address, because this will handle both types. So we can say format address. Yeah. Then. Yeah, so basically what we're saying is that the pointer is where the, this is, and this is the heap. And they should not be the same. If they're the same, something has gone awry, and they are not the same. So that's the stack one, and there's the heap. And we just showed like two different ways of getting to the heap. So the backing store, I mean. So this is approach 1.2, which is to, we can just do this. Approach, and this one is, we can just do like, there we go. So this basically gets us to the end of the addresses. So now what's left to do is, okay, now we know how to get the address of all of these things, which is handy, but now we got to deal with the size. So, and that is where the size of crate comes into play. So let's do that. Let's go to size. Okay, let's move that to the start. So what we're going to do is that here, let's write some comments. So, oops. Let's write some comments so that. So essentially, we have two different ways. We're going to try and use the standard library size of value macro, and I'm going to show you the limitations of that, and then we're going to look at the this one. Size of value. This is usually the same as size of type T. However, when T has no statically known size, when it's a slice or trade object, then size of value can be used to get the dynamically known size. So this is pretty handy to use. I tend to just use this when I'm using the standard library, standard :mem. But we're going to see very quickly how that's going to not be that great, and so why this crate even exists. We'll see that in a moment. So there you go. There's two different ways. And so this is the macro. Oh, it's not a macro. What do I say? It's a function. Oops. Okay, so let's do this. Let's write a test, and we're going to say get size of, something using standard library. And so let's grab those text fixtures. And then let's see, I think, let's see. Where is it? Okay, so let's do this. Let's start with scalar types. And then we'll do vex, and we're going to do structure type. So basically struct. Scalar type and I think it's compound types are the two different types in Rust. So let's make a byte, and this U8 is 1 byte, and the size of value, in this case it's sized, it's scalar, and then we can say size of scalar. We can use standard memory, size of value, and a pointer. We have to give it a pointer to the value, and that should give us, yeah. And then let's print it, and let's see if that works. lo and behold, size of scalar is 1 bytes, so that works. And then, so here, let's write some documentation for scalar type. So essentially things like usize, I32, things like arrays, tuples, and side structs. This will work. And in our example, this is just 1 byte. So yeah, this is 1 byte for U8. Let's, yeah, there we go. So that's the scalar. So now let's look at, like, what if it's vec? What does that look like? So let's make a vec. This one is going to be, I'm going to do U8s because it's 1 byte, so it makes the math super easy. And I'm just going to make something that takes up 100 bytes. 100 bytes in the backing store, plus the value, the size of the struct in the stack. So you'll see this in just a minute. So let's look at the size, let's see, of heap, of vec. Actually, I need to give it a better name, but we could say size of vec. This is really on the stack. We can say, this is not really size of vec. This is size of heap allocated without backing store. Yeah. So now we can do print line, and let's see what that comes out to. 24 bytes. So there's no way it's going to be, I mean, if you think about it, there's 100 bytes just here. So this is, so what is 24 bytes? If we run it again, let's see, it says 24 bytes. So what is 24 bytes? Well, this is 100 bytes. And this thing is 24 bytes. Why 24 bytes? Because it contains a few things. So let's see this. So for the vec struct itself includes the pointer to the heap allocated data. That's our backing store. The length and the capacity. And so it doesn't matter how many items there are, but the size of these three things is 24 bytes. So basically, it's like 24 bytes divided by, yeah. So basically, since I have a 64-bit machine, so which is 64 bits multiplied by 3. That's why it's 24 bytes. Equals, and so essentially, so here we actually, let's do this. Scale type. This is vec type. Yeah, so which is, so there's three words. This one, the pointer, heap allocated data, the length, and the capacity. Each one of these is a usize. So a usize in my case is 64 bits. My usize, and so it ends up being 24 bytes for this machine. This architecture, it's always going to be 24 bytes. So no matter if I change it to, like, you know, like 1,000, it doesn't matter. It's still going to be 24 bytes. So where did the 1,000 items go? Like, how does that work? So that's what we're going to do next. Let's see. So in this case, we're using the standard library. So what we could do for vec is that we could size the vec itself, and then we could go inside of the vec, because we know it's a U8. We know the length of the vec, so we could do some math. We could say get the size of the value. This gives us the 24 bytes, and then we can also say actually, let me do this. This is a bit more readable. And then we could then multiply that by you know, the length of the vec, which is 100, and then multiply that by the size of an f type t is usize, which in my case is going to be 8 bytes. Whew, that's a lot of math, but we could do it. But instead, I think you'll see the size of crate is much easier to work with. So we're going to be using that in just a moment. So let's put a pin on that. But let me wrap up this example with structs. So structs where we know the size already. So let's say that we want to do something like structure type, aka struct. We can do something like this. Just write some comments. Yeah. So let's make a struct whose size is going to be 4 bytes. So let's do struct my struct. So we have 1, 2, 3, 4. That's 4 bytes. And then we can do this because it's gonna, oops. Here we can do, let's get the size of the struct. And we're basically just creating a struct. And let's see, getting a reference to it, and then passing it to the size of value, and then we can print it. So that should be 4 bytes because each U8 is 1 byte and there's 4 of them in there. So yeah, 4 bytes. So that works, and it works as expected, which is great. And then, so we had this thing where how do I get the size of this vec? Because clearly it's not 24 bytes. It's 24 bytes plus 100 bytes, so it's 124 bytes. But it's recording. And how do we avoid doing all this complex math for something? It's tedious. It's not ergonomic. It's simple to do, but it's one more thing to do, and it's just kind of like cognitive load is increasing for really no good reason. So now we can use the size of finally the size of crate, and let's do that. Use super what is it, test utils, fixtures, and we can do, so in order to use the size of trait, we're going to have to import the size the size of crate. We have to import the size of trait because that brings into scope all of the goodness that we're going to be using in just a moment. So here we're going to repeat the same kind of thing that we did before, but instead of this standard mem size of val, we're going to do we're going to use this crate. So we're going to say let val, same thing, we just made a byte size variable. Now we're saying, okay, so this is interesting. So we say size of scalar is value.sizeof. There's a .sizeof came from the size of trait, and there's a whole bunch of trait implementations on all the scalar types that come out of the box in Rust and vec. So you can read all about it in here. So it's pretty cool. And there's even derived macros for your own structs that you make, the structures that you create. So this type is total size, which is I really I don't care about this. I only care about the total bytes. I don't care about this total size and how it makes this distinction, which is cool. You can use it if you need it, but for me, I just want to know the size. So I'm just gonna say get the total bytes, and let's print it. And this should be 1 byte. There you go, 1 byte. Cool. So now let's notice that the code is almost identical. I mean, it's not really any different so far. So let's do vec type. Vec type. So we're going to do similar kind of thing, but now we're going to say, actually, this is with backing store. So that's the difference, is that before it was without backing store, now it's with backing store, and also the size of the val itself, which is on the stack. So this is the total, the sum total of the size, basically. which is 124 bytes. Look at that. That's exactly what we were expecting. So this is size of heap allocated with backing store and stack. Basically the allocation of the vec itself on the stack. And let's see, heap stack allocated vec struct. That is a long variable name. So it's the sum total basically. So the previously we had like, so this is really not size of heap allocated. This is really size of stack allocated. Allocated vec, no backing store. That's actually a better name than because it is 24 bytes, and so it is those 3 words. Each word is for me 64 bits. So let's see. I think. Oh, actually, let's see. Let's also put in like. I like this. Let's do this. I like a slightly different formatting for this, so we can actually. This is size of vec, because it's the size of the full. What we think is size of vec, like what we originally were after. So size of vec of U8, which has 100 items, is 124 bytes. So that is exactly what we expected, and that is exactly what the size of crate gives us. So now, in addition to knowing the address of the vec, the vec struct on the stack, we also know how to get the address of the backing store, and we also now know how to get the size of just the vec on the stack and also the backing store, and then the combined size. So very cool. So this one is actually just I'm just going to make another struct, but this struct, my struct, same deal as before, but now I'm going to do something. I'm going to say my struct 2, and I'm going to make a struct 2, which is just going to have like 4 things in it. And now if I if I say derive, so if I tell it's a derived macro, the size of it errors out. It goes, oh, you have something inside which doesn't actually have an implementation of the straight. These do out of the box. These do, because they're scalar Rust types. In order to fix this, we just have to basically go to every single, like you can imagine a dependency tree, just go to every single child and make sure that every single thing implements size of. And so that's what this accomplishes. And then we can just put that allow that code thing in there. Okay. Now we can make a vec, and we can put a my struct and why this is red. That's weird. A, B, C, D, E, F. Oh, I see. So one thing, oops, let's undo this. So I should just read the error message. It's saying that it can't clone. And so, because if you notice, I'm replicating it 100 times. So what it's going to do is it's going to clone it 100 times and fill it in this vec. So what I need to do is I need to derive clone copy. So it's going to go red because this is not clone or copy. So then I got to go, you know what, let me do it properly. I'll do it from the bottom up. So all the reds don't, so this is clone and copy. So clone is a super trait. Copy is the subtrait. So anything that's copy is also clone, but anything that's clone is not also copy. Like vec is clone, but vec is not copy. U8 is clone and copy. So super trait, subtrait. I have a whole thing on traits in the videos I did recently on wonder why this is. Here it is. Rest subtyping and variance and rest lifetimes. This has all that stuff in it about subtraits, supertraits, and variance and all that stuff. So it's good. It's good videos to watch if you're wanting to know more about that. So here, again, I have to kind of ripple this through. So this also has to be clone and copy because this is clone and copy. Okay, now that our sample data is made, let's go find the size of this struct. So here we're just saying this vec size off is from the size off crate. We get total bytes, just like before. And now we should be able to do, actually, is that right? I think that's right. I think it, wow, Copilot did exactly the right thing. So let's do this. There we go. So the vec of struct, which struct contains struct 2, and there's 100 of these things, struct and struct 2, and combined they're 824 bytes, counting for the vec itself, which is on the stack, and these 100 items are in the banking store in the heap. So with that, we have come to the end of this video. I hope you enjoyed it. If you did, please give the video a thumbs up and subscribe to our channel, where you can be notified when I record new videos. Also, if you haven't already, we have a Discord you can join, and like right here. So if you have any questions, thoughts, comments, if you want to see other content, or you want to discuss any text user interface topics, stop by our Discord. And then check out developerlife.com. There's lots of really great articles. Some of these videos have associated articles, some don't. So, and if you haven't already, please subscribe to the newsletter. I only send out 1 or 2 a month, and it's usually with whatever new content has been published recently. With that, thank you so much for watching, and you will see me in the next one. Take care.